Oh, too far. Overcorrected. That's so bad. Hey everybody, Adam Savage here in my cave with the tooltip. I'm looking to crack open a bunch of discussion around this tooltip. And I wasn't planning on filming this weekend. This is supposed Thanksgiving weekend. My hair is funny. I wasn't planning on shooting this weekend, but this morning I woke up thinking about gauge blocks, and it led to a set of thoughts about tools, tool collecting, but even more specifically about the progression of knowledge when it comes to the making of things. Look, one of the most common questions I answer here in the cave when I do Q&As or I do panels at cons, a lot of people always want to ask about tool acquisition. And the question is frequently couched in many different ways, but it is essentially the same as what should I spend my money on? It's a totally reasonable question. If I want a Dremel tool, should I buy this one or that one? And which one will serve me better? And since all of our experiences are totally unique, that can be a difficult question to answer in the specific sense or even in the broad abstract sense. So I like to kind of zoom out a little bit. And my advice always is to buy the cheapest tool you can buy if it's a tool you don't know how to use. Learn how to use it and see if it integrates into your processes and into your shop. And then go and buy the best one that you can afford. And frequently that one will last you for the rest of your life. That is, in the acquisition of tools, that is absolutely my guiding philosophy. Now, I really want this discussion to how do I say this? I want to apply the philosophy I'm going to talk about today to everything. So I want to restate my definition of making, which is making is any time you reach out with your point of view and make something from nothing. So while what I do in here is very easily definable as making, I have run into many coders, photographers, writers who think of themselves as not makers. People in all sorts of different fields. And I submit that making is anytime you use your point of view to make something from nothing. That could be a poem, it could be a dress, it could be a book or a table. You never know. But how do I want to zoom out? When we set out to become better at a task, right, because making is not a static occupation. It's not a static thing. It's not like you told me how to make a paper mache stick figure and I'm just going to make that for the rest of my life. No. We make something, we get better at making it. We have a point of view about it. We progress. And that progression is the whole point of life. Seriously, that progression is the reason that we are here. When Monet painted the first Impressionist painting, Impression Sunrise, it was an intense thing in the world that it happened in. That was not what people did with painting. It's hard for us to recognize just how radical that was. But there was a critic at the time, I wish I could remember their name, but there was a critic at the time who went and saw Impression Sunrise and didn't understand it. And they said they kept going back to it because it didn't make sense. And then they explained that at a certain point, they had new eyes, and then they were able to see it. I love this idea about new eyes. And it's something that I'm addicted to. And I'm going to explain that you have almost certainly experienced it as well. So let's say you play the guitar. When you first picked up a guitar, it is a mystifying arrangement of tension, vibration, resonance, tonality, and you started noodling with it. But you didn't have any point of view about how stiff the strings should be or what the tonality should be. You were just playing. And then as you got better at playing the guitar or any instrument you have learned, the kazoo, seriously, it doesn't matter. At a certain point, you get past the beginner mode and you start having points of view and you start seeing what you can't do and you start trying to burn new pathways to learn how to do those things you can't do. And at each stage, you are gaining new eyes. So if you are a longtime guitar player, you understand information just by gripping the neck of the guitar and putting your fingers into a chord. There's all sorts of information being transmitted to you about how flexible the guitar is, what kind of strings it has, what kind of experience you're going to have with it. And none of this is stuff you could have possibly surmised the very first time you picked up a guitar. It's only from the iteration and the practice and the experience that you gained the eyes to be able to understand a guitar at that level. Same thing with a camera, same thing with driving a car professionally. Archery, right? That each of these, every discipline that you would undertake, that you could undertake and become better at, involves you being able to see new heights, and it's climbing. It is climbing. Chaim Potok wrote a book called The Book of Lights, about the enlightenment of a young Hebrew scholar. And they talk about the progression of awareness of the scholar of the Bible in terms of lights, that at each stage of awareness, new things are revealed to you, new lights. And it's like a stair step to enlightenment, right? That's what we're all trying for. So I have recently had that understanding within metrology. We're bringing it all the way back to gauge blocks now. I have had that understanding within the science of measuring things. And let me be really clear. The tool I'm talking about today, gauge blocks, is not a tool I am worthy of. And what I mean, that's not a value judgment. It's that my machining skills have not reached the point at which these are a highly necessary tool for me. They are a every now and then, maybe sometimes tool. But I do understand how they fit into the cosmology of machining that I do. And I didn't quite understand that before. And I would like to give you my understanding because, well, frankly, every time I understand something more about the world, I get a serious endorphin rush and it feels good. And I'd like you to feel the same rush. So let's talk about measuring things. Let's talk about measuring things seems to be like where science meets its total purpose because, well, you know, I can measure this sign that I liberated from a boathouse in Westchester County sometime in the 70s. I can measure this sign and I can tell you it's 12 inches by 22 inches. And I mean, those are facts, right? How could you dispute that this is 12 by 24 inches? I'm about to explain why that is not the actual measurement of this and why all measurement is a compromise of circumstance. All measurement. Yeah, it's really cool. Okay, so when you first start out making things, my guess is your first measuring implement was one of these. A 25 or 30 foot tape measure is absolutely one of the first sort of pro tools I had in my collection in the late 80s. And this is a great staple. Everyone should have one of these in their house. And there comes a time when you're learning carpentry where you start to actually measure not just to the line, but you start measuring to like one side of the line. Like these line divisors here, they have dimension in and of themselves. In fact, I dare say, I'll tell you that dimension in just a second. I mean, so yeah, it's like these lines seem to be about 20 thousandths of an inch wide, which means that my measurement of this is going to be plus or minus 20 thousandths of an inch unless I'm accommodating for the thickness of the measuring mark. The same issue happens at every scale where measurement gets more and more refined. So that when you achieve a certain level of mastery of machining, the machinist equivalent of the tape measure is the 6-inch dial caliper. This is the bread and butter tool of the beginning machinist. Everybody has a rite of passage as to their first dial caliper or their first digital caliper. 6 inches is absolutely the most common size. They make these in 4, 3, 8, 12, 24, but 6 inches is really, and by the way, I'm not sure they make a 3-inch. I just really want a 3-inch caliper. Anyway, this is the tape measure for machinists. And this measures to 1,000th of an inch. So every little mark there is telling me that these jaws are 1,000th of an inch greater farther apart. And the great thing about these dial calipers is they can measure an outside dimension, they can measure an inside dimension, and they can measure a depth dimension within reason. For if absolute accuracy is super critical for you, like high accuracy, you wouldn't want to use these for any of these measurements. They get you in the ballpark. They get you plus or minus 1,000th of an inch. And 1,000th of an inch seems like a pretty small distance. It's about the thickness of a rolling paper, give or take. It's about 1/4 the thickness of your average sheet of paper, about 1/3 the width of your human hair, give or take. 1,000th of an inch seems like a very small increment. However, anybody who's ever bored out the cylinders on an engine block or done like significant repair on a mechanical device, 1,000th of an inch can get you into a lot of trouble. And there are frequently occasions in which you want far greater accuracy than 1,000th of an inch. And when you do, well, you move on to, let's see. When you want even greater accuracy, you move on to something like this. This is a gauge that goes to 1/10,000th of an inch. And 1/10,000th of an inch is 2.5 microns. And a micron is 1,000th of a millimeter. All right, so we've established that we're in these very, very small increments. In fact, this gauge, which I've just bought, and just like the gauge blocks, I'm not worthy of this gauge yet. This gauge has a ruby ball on its end, highly stable, hard gem, just like the same way they use rubies as the bearings in high-quality watches, like this one. For high-quality measuring equipment, it may very well be the ball end of such a thing. And this will measure every single measure. Okay, here's how precise this gauge is. 0 and the 1. That 1 is 1,000th of an inch. Yeah. 10 divisions for 1,000th of an inch. So it measures to 1/10,000. And I can see where I am on either side of that line. So this can give me micron accuracy. But this, as you notice, this device doesn't have 2 jaws. It only has 1 feeler. Well, how do you use it? So this is the point at which I explain that when you get to super refined measuring of things, you no longer measure it directly, you measure it comparatively. Yes, at a certain point, when accuracy is paramount, you don't measure empirically, you measure comparatively. And I'll show you what that means. Okay. So this here, the floor here, is a ground marble block. It's what's known as a reference surface. It has been lapped to a certain degree of flatness across its width. And all metrology at a high level involves reference surfaces like this. Now, when I place this gauge on a little gauge stand here, let us say I wanted to make sure I had ground this parallel to precisely 3/4 of an inch. So you see it right here. I've got it dialed into 0 on my gauge, and the gauge is reading the top of the parallel. And if I move this back and forth, the dial doesn't move. It actually shows you just how finely ground this is. Oh, yeah. Every time I even tilt it the littlest bit, the measurement goes kablooey. But that is a finely ground surface with a high degree of parallelness. But if I want to check it, well, that's when I break out a gauge block. Now, this gauge block has been lapped on its flats to be precisely 0.75 inches thick. So I can use this as a check against this. Now, before I do it, I clean it. I make sure that it is free of oil and dust. I make sure to not drop these. These are Cera blocks. But watch what happens when I put one underneath here. You should see it go right back to 0. There we go. So what I can tell you is you can see just how well made these blocks are. There's no movement at all. And what I've learned now is that this is 2/10,000ths of an inch taller than the reference block of 3/4 of an inch. Roughly 5 microns, give or take. 5 microns. So, I have here in front of me a ground marble plate. This is called a reference surface. It is a reference surface because it is flat and it has been certified as flat from the factory within X across its length. So sometimes the low grade versions of these are ground to, I don't know, 1,000th across the width. I don't actually even know what the standards are on these. But when you buy one of these surface plates, and they can be marble, they can be cast iron, they can be steel. When you buy one of them, it is certified at the factory to be flat within a reference point. And then you use that to do things like make your milling machine super flat and to scrape the ways and all those things that you might do. But again, instead of measuring between two sides of a single tool, I am using this reference surface as a common flat against, and this gauge, which goes to, as I said, 1/10,000th or roughly 2 microns. I am no longer measuring something like this. I am comparing it. So I have here a ground parallel for my milling machine. It is 3/4 of an inch high. It is this distance. So when I bring it in here and put it under the dial, you can see, yeah, now I've got to, yeah, everything moves. Everything moves. All right. Wow. All right, there we go. Okay, now I've got it set to 0. And as I move, it doesn't move very much. There we go. But how do I make sure that this is precisely 3/4 of an inch in diameter when I've told you I don't trust these with the high degree of submicron accuracy? Well, that's when I use one of the gauge blocks. So this is a 3/4 inch gauge block. It has been calibrated to be plus or minus 3/4 of an inch. Actually, wait, I can tell you from its certification sheet. The 3/4 inch gauge block, hold on. .75. Hang on. 0.75. When you buy a set of gauge blocks, it comes with a chart. Each block has been calibrated. And my gauge block, the 0.75 gauge block, is calibrated to a variance of 2.7 microns. Uh-huh. They have looked at its maximum deviation from the norm and its minimum, and 2.7 microns. So I am going to use that gauge block to see just how close this is now that this is at 0 to 3/4 of an inch. And I put it under there, and I am 2.5 thousandths under, which means that this is 2.5 10,000ths, which is roughly 5 microns, give or take. Actually, it's pretty close. And given that this had a variance of 3.7 microns, like we're in that, you see where we are, okay? Are you getting the I'm not doing this as a lesson in how to use gauge blocks. I really just kind of want to get our heads wrapped around the same concept before I move on. So you understand the gauge block is used as a, again, just that this plate is a reference point that's perfectly flat, so too these gauge blocks are reference points. But do you only use them in and of themselves? No. The gauge blocks come like this. Almost every modern set comes like this. And there is a reason for the increments. There's 50 thou, 100 thou, 1,001 thou, 1,002 thou. The dimensions of each of these has been calibrated as part of a mathematical formula that basically, with this combination of blocks, you can combine them, and there's a formula for doing it, to make any measurement reference you want between 50 thousandths and 3.99999 inches. Yeah, 4 inches plus or minus a 10th thou, I think is what I just said. So this means that the gauge blocks aren't meant to, hold on just a second. There we go. We're really getting in the weeds. This means that the gauge blocks aren't just to be used as references in and of themselves for their sizes. They can be combined. Let me take off my watch. How do you combine them? Well, let's say I wanted to add a 750 thou to a 250 thou and make myself a 1 inch. Let's see here, which one is 250 thou? I think it's this, right? Am I right? No, it's this. It is that. Okay. So, so let's say I wanted to join together the 750 and the 250 and give myself a reference of 1 inch. Now, there is a 1 inch block, but I'm making a point here. Now, first off, you want to make sure that there's a very light coating of oil. Oh, whoops. I have not yet used my Starrett light tool and instrument oil. Actually, let's take a little bit like this. Just the tiniest coating. Actually, I'm going to bring this over here. The tiniest coating of oil is one of the ways in which these operate. You put a little oil on and wipe it off. Now, how do you combine the gauge blocks? Machinists know where I'm going with this because it is an amazing thing. How do you combine these gauge blocks? Okay, you combine them. Forgive me. Yes. Okay, you combine. How do you combine these gauge blocks? Well, you don't just do that. Because you don't just do that. You actually join these together to a process called ringing, and it is kind of mind-blowing. Here is ringing. With cleaned blocks that have the lightest possible coating of oil on them, you join them at 90 degrees, and while pushing, you turn them, and when you do, they stick together. That's because of how flat they are. Hold on, I'm gonna show this to you. It's not as impressive with the two measurements I've just shown you. So I'm gonna actually change these and move on. I'm gonna do 0.75 and the 1 inch. Yes, here we go. So again, I'm gonna get just a tiny bit of oil on the sides to be wrung. And on the gauge blocks, the distance is here, from here to here, right? It's across there. So when I join these two, I will end up with a reference block of 1.75 inches. Here is ringing. Bring them together at 90, twist, under pressure, and let go. And it is literally the surface tension of the flatness that keeps them together with a little help from the oil. I do believe the physics of exactly why ringing works is still under some dispute, but so is the aerodynamics of wings. We've got a lot of work to do. Suffice to say that the distance in the middle here between these two blocks, I've just read this extensive scientific paper that talks about that distance is a reliable 25 nanometers. I've been talking about thousandths of an inch, which I explained are, I've been talking about thousandths, I've been talking about microns. I know I'm bouncing back and forth between standard and metric, but all machinists do, frankly, seriously. I know mostly American machinists, but I've been bouncing back and forth between inch measurements and metric measurements. Then I just offered up a nanometer. So if I say the distance between these two blocks is 25 nanometers, what does that mean? Well, a nanometer is 1/1,000,000th of a meter, which means that given that a micron is 1,000th of a meter, a micron is 1,000th of a millimeter. Sorry, I'm getting this wrong. Hold on a second. A nanometer is 1,000 microns. Am I right about that? Alexa, how many nanometers are in a micron?
1 micrometer is 1,000 nanometers.
There we go.
By the way, Cyber Monday deals have already started.
Alexa, stop. Slow down. Sorry. I'm hoping that Joey or Norm, whoever's editing this, will make it a little clearer. So, I've been talking about, I'm going to go back to the beginning of this. So, when I ring these together, what's the difference between ringing them and just placing them together? Well, the different one is they don't stick, but that's not the biggest reason. The biggest reason is that when I ring them together under pressure, not only does surface tension hold them together, but the distance between them is knowable. That is the space between the two blocks, even though I've joined them together and pushed them, and they are incredibly flat, like they're way flatter than anything you've experienced in your life or me. Even though both of those things are true, there is still a distance between this block and this block, and it needs to be known. And I just read this extensive scientific paper which explained that the distance between these two blocks is reliably 25 nanometers. Nanometers. I've been talking about inches, thousandths of an inch, microns. A thousandth of an inch is 2.5 microns. What's a nanometer? A nanometer is 1,000th of a micron. The first time I learned what a micron was, 1,000th of a millimeter, I was like, yeah, like I'm ever gonna need that. And now I'm regularly machining to, about a 10 micron, 20 micron accuracy. But a nanometer? What is a nanometer? I'm gonna give you a practical example of what a nanometer is for you. A nanometer is the length your fingernails grow every second. Yeah. Yeah. Sorry. I might have said earlier that a nanometer is a millionth of a meter. It's a billionth of a meter. Yeah, it's a millionth of a millimeter. Right. 25 nanometers. The distance between these two blocks is the length your fingernails grow in just about 30 seconds. Okay. I know I'm getting deep into the weeds here, and we're going a little bit farther. Because when you set up something like this and you measure it on a reference surface and you compare it to something else using a surpassingly accurate gauge like this, you still have not answered the question of how big the thing is. How come? Because of heat. Because of heat. Heat matters. Huh. Okay, so when I got to put these gauge blocks back, I'm terrified of tipping them over. So you unring them just by twisting them back and pulling them apart. It is literally like magic. The amount of pressure between them, the stiction force is surprising. It's genuinely surprising. So I've just gone all this way to say when you want to measure stuff really, 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 really crazy carefully, you go to these guys. And then I said, even though I've compared a measurement to these guys, I still don't know exactly how big the thing is because of heat. So all of these, this certificate of inspection in which every single one of these blocks was tested in a facility for testing the nanometer accuracy of these guys. That has all been done at 68 degrees Fahrenheit, plus or minus 1.8 degrees. All of these measurements are only measurements that you can count on if the ambient temperature in your shop is within, within 1.8 degrees. So you can only use these as reference measurements that you can count on 100% if they are being measured at exactly 68 degrees Fahrenheit plus or minus 1.8 degrees. Yeah. Okay, look, I just built a thing. I just built a thing in which I was, okay. Let me get to the big scale here. Everything expands and contracts because of heat. Everything. Everything in the world expands and contracts because of heat. The main cables that hold up the 4,000 plus foot long Golden Gate Bridge, the main cables that hold it up are 16 feet longer in the middle of the day under bright sunshine than they are in the middle of the night. That's how much steel can expand. Now, those main cables are probably 6,000 feet long, 5,000 feet long. I don't know. I haven't done the math for a catenary curve, et cetera, on a suspension bridge, but I know the bridge is about 4,500 feet long. So whatever those cable lengths are, they are 16 feet longer in the middle of the day than they are at night. That's because steel expands and contracts. You might think it's a surprising number. It was surprising to me the first time I heard it, but I still would imagine when I'm in my shop making something like this, how much does heat matter? Well, when I'm measuring the internal dimension of this, if I've just machined it and it's hot, I'm going to get a substantively different measurement than when it's cold. And that can lead you to some really difficult problems as a machinist if you're not accommodating for that. And this is the last place I want to go, because if I am machining a piece of steel, these ceramic blocks, which are incredibly stable. They're way more stable than steel. That is, they expand and contract less under thermal conditions, under variant thermal conditions. They expand and contract less than steel blocks do. And while that sounds like it's ideal because we all kind of live in a mental world where things are one measurement or the other measurement, they are black or white. We try and separate the world into categories that we can parse. That's what science roughly is. So it would seem that if I have a reference that is stable, that's fantastic. But there are occasions in which it is not, because if I am machining steel and I use a set of steel gauge blocks, these are far less accurate blocks. I don't even think that they've been hardened. I think they are simply ground and lapped. These were like, sorry, let's just be clear. This is a grade 0 set of Serra blocks that was a gift to me from Mitutoyo for some of the videos I made last year about my antique Mitutoyo equipment. They asked me if there was something that I wanted. I said, I am not worthy of most of your tools, but I would happily be the steward of a set of Serra blocks if you had them. And they did. They sent me this. And this is thousands of dollars. This is a tool I would not have tried to afford at this moment in time. I don't think I'm worthy of it, but I love having it, and I am starting to get, as I said at the beginning of this video, I'm starting to get to know how to use this. However, for practical machining of steel blocks, I need a bench, like a workshop set of gauge blocks. This is like $300. It has the same distribution. It also comes with a chart of exactly how accurate these gauge blocks are, and no surprise, they're actually far less accurate, far less like tight to their dimensions than the Sarah blocks are. The advantage that the steel gauge blocks have is that they're steel. And if I'm working with steel, I don't need to do any adjustment for temperature in the room. Because the reason the Sarah blocks are accurate plus or minus 1.8 degrees Fahrenheit is that a few degrees Fahrenheit can cause these blocks to expand or contract by a few nanometers. And they've already been calibrated within a few nanometers. So those they're only going to stand by those calibrations at a specific temperature. And if submicron nanometer accuracy is absolutely critical, and for certain things in the medical industry and like high precision tiny nano machines, it absolutely is, you have to accommodate for the temperature in the room. And if you're working with steel and you have steel gauge blocks, you don't need to worry about the calibration because they're both under the same conditions. So if it's 75 degrees in here and I'm working with steel, I can be assured that the steel I'm working with is expanding and contracting to roughly the same amount that the gauge blocks are, and thus I can just use these rather than having to make an adjustment. I know, this was like, I really hope this was clear, or at least somewhat clear. For me, the understanding, oh, right, let's talk about my central understanding at the end of all this, because this came about from reading this like 30-page paper on gauge blocks. Sorry, by the way, gauge blocks were invented by Carl Edvard Johansson in 1896, and they really, really, really helped push forward the Industrial Revolution because they allowed for a repeatable, reliable metric by which two different shops could make something and be assured that those two things would work with each other. Yeah, that's significant. And I mean, like, there are stories about like they made like 100 sets at the beginning and they were surpassingly expensive. And then they figured out ways to lap them and make them less expensive. But even still, the ceramic blocks, you know, a really high quality set can be thousands and thousands of dollars because of the precision that has gone into their manufacturing and their calibration. All of this comes into my head, and the conclusion I come to is there's no such thing as an actual measurement. That was a weird noise. I am like a bull in a china shop. There's no such thing as an actual measurement. So early on in Mythbusters, we were doing an episode about swimming in syrup. Is swimming in syrup just as fast as swimming in normal water? Because, and the myth is that it is. Because while you have a thicker material to push through, you have a thicker material to push against. And those two forces cancel each other out. And thus, in the myth, as stated, you can swim just as fast in syrup as you can in water. We tested it. And we found out that it's true. But that's not the point of the story. The point is that when we were first researching the fluid dynamics of syrup, et cetera, I found out, well, I knew that this whole episode intersected with viscosity. I knew viscosity was a concept we had to talk about. And so I found out that the study of viscosity is called tribology. I found out that there was an international what do you call it? House of Tribologists, International Association of Tribologists. There's a president of tribologists, and he has a phone number on the website. And I called his phone number, and he picked up. And I said, "Hey, I'm Savage. I work for Mythbusters. I'm doing this thing about swimming in syrup, and I want to do an analog test." I told him about viscosity, and like, is that as simple as me just taking a jar full of a liquid and poking a specific size hole and timing how long it takes for the liquid to run out? And in his response to me, I could tell he was a little upset. And the reason it turned out, as we began to talk about it, is because my question was not even wrong. I was thinking of viscosity as a specific quantifiable property of a liquid. Let's say it's maple syrup. I was asking him, how do I tell the public in an analog test how thick this syrup is? And the problem is that that's not how viscosity isn't a singular value you can give to something. Viscosity is a relationship between the liquid and all sorts of environmental factors. The kind of vessel that it's in, the sort of pressures that it's under, the heat that it is under. This is why motor oil for your car is a range. It is a range of viscosity. It's not a specific viscosity because it has a range, whether it's cool or warm. So my question about an analog test for an absolute value was not even in the right ballpark for the way he professionally understood viscosity. And he gave me a deep understanding that afternoon. And it wasn't until this week when I was reading the papers about gauge blocks and trying to wrap my head around them that I realized that all measurement effectively falls under the same blurry outlines, which is, look, we don't have any trouble, all of us, agreeing that this is 12 by 24 inches or whatever the hell I said it was. We understand that the measurements that I gave for this are reasonable and tight within parameters that we would all need to know to work with a sign like this. But when we get really precise and we say, how big is it? The answer is, well, it depends. And the idea of, well, it depends, is a reasonable answer to give for a piece of steel that is 4 inches long, and it might be 4 inches and 20 nanometers at one temperature and 4 inches, 3.99995 inches at another temperature. I find that an endorphin rush. That's the thing. I find that I get an endorphin rush from that level of clarity, that the closer you look at stuff, the harder it is to measure. And there's a classic map makers thing of you can't measure a coastline too carefully. Like what distance are you measuring it at? 1 mile off the ground? 100 feet off the ground? 1 inch off the ground? All three of those, as you trace the path of water around a shoreline, are going to change. I mean, also because a shoreline is fractal, and the deeper in, the more detail you're going to see. The same applies across all, the same rules apply across all measurement. So science is always about looking in finer and finer increments at the world and the universe and the fundamental building blocks of them in order that we may understand the grammar by which all this stuff runs. The most surprising and thrilling thing is the deeper you go, the more interrelated everything is. The more all things and their measurements and their values are interrelated to their environment and the things around them and their conditions that they're under. And I find that strangely reassuring and beautiful. Because again, when a superior machinist is trying to achieve a perfect fitment between two parts, whatever perfect fitment means for that project, the measurements only get them so far. Because they need an understanding in here of how those measurements interrelate, both environmentally and specifically, in order to achieve the precision that they're looking for. And I know this has been like the longest tooltip I have ever done, and I hope it's not too deep in the weeds. I just wanted to give you guys a little bit of like that endorphin rush that I got when I understood it. I'll try and find this paper on the metrology of gauge blocks, and so we can post it in the comments below. Let's say that paper that I've been talking about this whole video, a link to it is in the comments below. Thank you guys so much for joining me on Tested for this tooltip. I would love to know some of your favorite measuring instruments. And look, I am also positive that I got some terms wrong within this video. I hope you guys will give me some forbearance for that, because I'm not talking about the science of metrology specifically. I'm talking about the philosophy of it. And so I tend to be a little loosier and goosier with my nomenclature when it comes to researching a video like this, as opposed to when I'm trying to do a how-to. I almost never try and do a how-to. All right. 18 minutes, 23 minutes just for this tape. Thank you guys so much. I'm Adam Savage. I'll see you next time. One of the things I love about this channel is that we don't make how-to videos so much as we make what happened videos. And what almost always happens are mistakes and screw-ups. In fact, they're completely integral to making and honestly to being a person. And to celebrate this, Tested has a new batch of demerit badges for the screw-ups you will encounter in the shop. From left to right, we have touching your paint job, assembling things backwards, losing a tiny screw or part, gluing your fingers together, and smashing your thumb. And frankly, if you haven't done both of these, even if you're not a maker, I just don't feel like you've experienced enough of the world. I'm not saying get out a hammer and smash your thumb, but I will tell you that the blacker your fingernail after the injury, the less it's gonna hurt in the long run. I almost forgot, these make excellent additions to your shop apron, and they are available at tested-store.com.